Hello, my name is Itay Safran. This is joint work with my PhD advisor, Ohad Shamir, and it's called How Good is SGD with Random Shuffling. We consider the following optimization problem where we optimize over finitely many convex functions, where their average is strongly convex and each individual function is smooth in Lifshitz in a bounded domain, and where we consider a fixed step size eta. Our goal is to bound the suboptimality rate, which is the expected difference between the value attained at the optimal point and the value attained after k epochs of the SGD algorithm using different various sampling methods. The sampling methods we consider are the following. We have the well-studied and well-known with replacement sampling, where at each iteration we sample an individual function uniformly at random. This setting is very well understood, and the main reason is that by sampling each function uniformly at random, we have that this provides an unbiased estimate of the gradient at each iteration, which greatly facilitates the analysis of the algorithm. However, much more popular in practice but less understood in theory are the without replacement sampling techniques, which include the iterative gradient method, which is just sampling all the functions in some fixed deterministic order and repeating that order at each iteration, at each epoch. Using some more randomness, we have the single shuffling sampling technique, which basically draws some random permutation of all the functions at the first epoch and repeat that random permutation across all the epochs. And we have the random reshuffling sampling technique, where we draw a random permutation at each epoch again and again. These are the known suboptimality rates we have for these kinds of sampling techniques. First, for with replacement, we have a very well-known result of 1 over nk suboptimality rate, which is also known to be tight. For the without replacement sampling techniques, there were recent breakthroughs in recent years, which showed, beginning with the iterative gradient method, that we obtain an upper bound of 1 over k squared, which also implies such a bound for single shuffling and random reshuffling. Also, the authors show this is also a lower bound under the assumption that we only consider two functions, and that this bound is also asymptotic in K. However, it would make sense that for other sampling techniques, namely single shuffling and random reshuffling, the bound should improve with the larger number of functions we have. And this was indeed what was shown by Ohad Shamir. So we do get that for just a single epoch, the bound improves with the number of functions, but it is not clear what happens when we perform more than 1k epoch. Then we have the following result by Hao Chen et al. And what they showed is that we do get a bound which improves both with n and k, depending on the ratio between n and k. And later on, another result was shown, which is stronger, assuming that k is not too large, which is typically the case, since we don't perform very many epochs, and usually we have much more functions in our objective to optimize. So these bounds indeed show that we do get better suboptimality rates for more functions and more epochs, of course, but the exact suboptimality rates has remained elusive. And our main contribution in the paper is to show the following lower bounds. We show for the iterative gradient method a lower bound of 1 over k squared. This bound is non-asymptotic and works for all n. For single shuffling, we show a lower bound of 1 over nk squared. And for random reshuffling, we show a lower bound of 1 over n squared k squared plus 1 over nk cubed. So again, we see that depending on the ratio between n and k, we get different asymptotic behavior for the suboptimality rate of random reshuffling. Additionally, if we make the strong assumption that the functions we optimize over are univariate quadratics, then we also show that the lower bounds we have for single shuffling and random reshuffling are in fact tight. That is, they match the lower bounds we derived. Now I want to discuss our lower bounds in more detail, and to do so I first want to discuss the assumptions made when deriving them. As I previously mentioned, we run our algorithm on n individual functions, and we do this for k epochs. The average function of all the individual functions, which is our objective, is assumed to be lambda strongly convex. We assume each individual function is convex and quadratic. Remember that the more assumptions we have in a lower bound, in fact, the stronger that lower bound is. We also assume that each such function has lambda Lifshitz gradients, and that it is G Lifshitz for any x in the neighborhood of the optimal point. We also assume that we initialize our algorithm in such a point which satisfies the previous assumptions. This is the result we have for the iterative gradient method, the lower bound we got for it, assuming that k is at least 1, that n is at least 2, and that g and lambda satisfy this mild inequality. Then we can construct a function which is univariate, and we have some initialization point x0, which is not too far away from the optimal point, such that the iterative gradient method cannot attain a convergence rate which decays faster than quadratically in k. To obtain this result, our construction is the following. We consider half the functions, n over 2 functions of the linear form we see here to the left, and we consider the remaining half amount of functions, as the functions we see here to the right, these quadratic functions. And first, the algorithm, since it's deterministic in order, it performs iterations over the functions seen to the left, which throws the algorithm to the left roughly n times, which costs us at a convergence rate which does not decay with n. For the single shuffling case, we have under very similar assumption that if we run single shuffling SGD with a fixed step size, then we cannot attain a convergence rate which decays faster than 1 over nk squared. The construction we use is similar to the previous one. However, we have quadratic functions shifted to the left, here in the left, and quadratic functions shifted to the right, seen here to the right. And they average to the functions seen here in the middle. And these set of functions allow us to derive the bound we see here in this slide. For the random reshuffling case, we have under similar assumption to the previous theorems, that we can construct a univariate function and an initialization point such that the random reshuffling SGD algorithm with the fixed step size cannot attain convergence rates which decay faster than magnitude of 1 over n squared k squared plus 1 over n k cubed. To achieve this, we use two constructions. One is similar to the construction used in the iterative gradient method bound, which provides us a lower bound which decays at the rate of 1 over n squared k squared. And on the other hand, we have a similar construction to the one used in single shuffling, where we cannot attain a convergence rate faster than 1 over n k cubed. Combining these two together derives the final result we have, where the average function, the objective function we optimize over, is seen here in the middle. Moving on to our upper bounds, we assume the following assumptions. We again run our algorithm on n individual functions for k epochs. Again, we assume that our target is lambda strongly convex. And here we would assume, to facilitate the analysis, we will assume that each individual function is univariate quadratic. It is convex. It has L-Lifshitz gradients, which is also a common assumption in the literature. And this holds for any iterate x throughout the algorithm. And we derive the following theorem for single shuffling SGD. Assuming that we have the following inequality which holds, which is n times k over the log of nk needs to be at least the Lifshitz parameter L over lambda. This is the condition number. This quotient is the condition number, and it's a common assumption made throughout the literature. And if we assume that we have the following step size, which we see here, then we can provide a guarantee that the suboptimality rate of single shuffling SGD will decay at a rate of roughly 1 over n times k squared. This, of course, matches the lower bound we derived. And here we also omit logarithmic terms. For the random reshuffling case, we have the following theorem. If we make very similar assumptions on the condition number and we take a very similar step size, then we can guarantee the following convergence rate. Well, note that, again, this matches the lower bounds we got, and very interestingly, in some very recent work that was just published after we published our paper, the authors there derive such a result for multivariate quadratics, establishing that our bound is essentially tight also in the multivariate case. So, to conclude the talk, this is our take-home message. When we optimize over finitely many convex functions, then the more randomness we introduce into our without replacing sampling, the provably better its expected performance is, at least in this simple regime where we assume that the target function is strongly convex and the individual functions are convex. Thank you very much.